Today we're going to be covering how to interpret logistic regression coefficients. Okay? So does anyone have any inkling on how to do that? Has anyone ever seen an interpretation of logistic regression coefficients before? No. But that's fine. That's why you're here to learn. If I tell you instead how do I interpret the regression coefficients on linear regression, do we know how to do that? Yes? I see some nods. Does everybody know how to do that? No. Some people don't say no. Okay. So that's a good point to start at then. So let's say I have a linear regression model of the following form. Right? How do I interpret alpha?
Intercept.
It's the intercept, which means, what does it mean?
X is 0, this is the value.
Yeah, this is the value of the expected value of y when x is 0. Exactly. And beta?
It's a coefficient.
That is correct. And what does it mean?
And like it's just when. Yeah, like
How
the
steep?
gradient.
Yeah, it's the gradient. Exactly. So if you had to explain it in words, you would say for a 1 unit change in x, we would see
A beta, like change in y.
perfect. For a 1 unit change in x, a beta change in y. Okay. So this is how you interpret linear regression coefficients in a very simple sense. The nice thing about it is that they are linear, which means they have this interpretation of a 1 unit change in x for a 1 unit change in for a beta unit change in y. Logistic regression coefficients are not like that. So that sucks. And so we have to learn a different set of rules to interpret logistic regression coefficients. In order to learn those rules, we're going to have to cover some quantities that are related to probability. Okay? So if I tell you what is a probability, you might say, what is a probability? Some of you even asked that question on the Q&A.
The likelihood of something happening.
Perfect. The likelihood of something happening. It varies between 0 and 1. If you're close to 1, there is a high likelihood of something happening. If you're close to 0, there is no likelihood of something happening, right? Everybody on the same page there? Yeah, okay. You can express this likelihood in a slightly different way, a way we call odds. Who of you bets on the, bets on horses or MMA fights or football? You bet on horses?
I bet on football.
Football, okay. I mean, football, horses, it's all the same anyway. And so odds are a different way to express the concept of probability. Namely, they are the probability of an event happening divided by the probability of the event not happening. So you might say, for example, an odds of 2 means the event is twice as likely to happen as opposed to not. It's 100% more likely to happen than not. If it was an odds of 1, what would it say? What might an odd of 1 mean?
It's definitely happening.
It's definitely happening? So if the probability of...
Oh, it's 50-50.
It's 50-50, exactly. There's a 50% probability of happening. There's an equal chance of it happening as opposed to not, right? And an odd of 0.5?
There's a 25% chance then, because it halves?
Yeah, exactly, yes, exactly. So there is, the probability of the event happening is half the probability of the event not happening. Exactly. Okay, great. So that is odds. Now, these are measures, probabilities and odds are measures of likelihood, right? How likely something is. But sometimes we're interested in comparing measures of likelihood. So is an event more likely to happen for you than it is for you, right? Is it less likely to happen for you than it is for you? And so we have to introduce a series of metrics to account for that. So the first metric we look at is called risk difference. Now you should know that probability is also called risk in terms of epidemiology. So we refer to risk and probability as the same thing. The reason is, in epidemiology, typically, which studies the development of disease, right? We typically look at models of disease, and so we say, if there is a high probability of you developing the disease or dying, there's a high risk. So risk and probability are used interchangeably here, okay? So one measure that we like to use is risk difference. So what do? We take a reference category. So I'm just going to say the average person in the Netherlands is my reference for whatever we're looking at. And then I have a subject's risk. So let's say your risk. And then I want to compare your risk against the reference. And then I say your risk minus the reference risk is my risk difference. So if you have a risk difference of 5%, it means you have a 5% higher chance of developing the disease or of voting for Trump than the reference, for example. Okay? Another measure, so this is a nice measure because it's easily interpretable, right? It's like 5% is the difference, right? Okay. Another measure that is more useful, especially when we have very rare events, is the relative risk, also known as risk ratio. Why do I say it's useful for rare events? Because suppose that the reference value for developing a very rare disease is like close to 0, like 0.01, let's say. And then your value for developing the disease is 0.02. Well, the risk difference is going to give me a difference of 1%, but actually you are twice as likely as the reference to develop the disease, right? So when the event is quite rare, it is useful to work with relative risk as opposed to risk difference. Does that make sense? Who's confused? Nobody's confused. Okay. Confused.
I'm not sure. You said risk difference is risk for an individual event minus the what?
The reference risk. So some reference. That could be the average person in the Netherlands, for example.
Ah, okay.
Yeah. And then relative risk is your risk divided by that same reference.
Oh.
Yeah. And so these two are nice because they work with probabilities or risk directly, but then we want to work with odds as well, right? And what we have to work with odds is the relative odds, also known as odds ratio. So, and that is just the odds of an event happening for you divided by the odds of the event happening for the reference, right? So again, same story. We put a reference at the bottom, we put you at the top, or the subject of interest, and then we divide, and we find out, okay, your odds of developing a disease are 2 times those of the reference, or they're the same as the reference, in which case the odds ratio would be 1. Who's with me? Does it make sense? Who has doubts? No doubts. Clear as sky. Okay. So now we try to bring in, why am I bothering you about odds? It is because, you remember in the last lecture we spoke about the fact that the linear model is linear. What does linear regression model, the Gaussian model, is linear. What does linear mean? What does it mean for a model to be linear? You can do this. Okay, yes. And in terms of the parameters, do I add the parameters? Do I multiply the parameters of the model? What do I do?
You add or subtract.
You add or subtract. They're additive, right? A linear model is additive in nature, exactly. And so that's why we have alpha plus beta x, right? This is a linear model, right? This would be different if I had alpha times beta x. That would be a multiplicative model. It wouldn't be linear anymore, right? And the thing about logistic regression is that it is nonlinear. So when it is linear on the log odds scale, also called the logistic scale or logic, but it is nonlinear on the probability scale. Let's walk through that. So, firstly, do you recognize this? So if I tell you the logit of pi is equal to the log odds of pi, does this look familiar? No, it doesn't. Okay. So pi, you know, as the probability, right? You remember the inverse logit function that is used to go from a probability from a linear model to a probability. Do you remember that? We covered it on Tuesday, yes? So if I have mu equals alpha plus beta x, then if I can say that pi is equal to the exp of mu divided by 1 plus exp of mu. Does this look familiar? It's also known as the logistic sigmoid. For whom is this totally new? You can tell me. This is the time for you to ask questions, right? So is everybody on board with this? You need to tell me if you're not. You're not on board with this. Tell me exactly what it is about it that looks totally unfamiliar. So mu, you understand. It's the linear model, right? Then we have the probability, pi.
So it's like the average?
It's the expected value. In a linear regression, yes, it's the expected value. Yes, right? Which is if we're having a linear regression model, it would be the average, right? for a given individual, right? So this would be mu I and x I, right?
Oh, x is expected.
Exp is not expected, exp is exponential.
Exponential.
Yes.
What does it mean?
So it means, what does the exponential mean?
Yeah.
So, you know, this is a linear, this is a line,
Yeah.
right? If I take the exponential of this line, it'll look something like this, right? So it's you know, the concept of like exponentially increasing. So it's a function that you apply to data in order to, it's a monotonic transformation of the data, which means it doesn't change the order of it, it just changes how distant each point is from each other. So in this one here, the points are kind of nicely, neatly aligned, right? In this one here, this point is here, this other point is here, this other point is here, so you can see the distance has changed here, even though the order has remained the same. Okay, so what we do typically is we work on the log scale. The reason we work on the log scale is because the log scale tends to be linear. So that's why we have, in logistic regression, we work on the log odds scale, which allows us to express probabilities in terms of linear functional parameters. Did you understand what I just said?
Yes.
So the log odds scale allows us to express a probability in terms of a linear function of its parameters.
Yeah.
But now that we have done that, we need to take that log odds scale and turn it back into a probability.
So it's like mu to the power of mu.
It's e to the power of mu, like
Oh, okay.
divided by 1 plus e to the power of mu.
So that's the same thing.
Yes.
Okay.
Are you familiar with this?
Yes.
Ah, okay, good, excellent. So you're just not familiar with the exp notation. Okay, that's good. That's fine. You can think about it as this way. Okay. So this is also called the logistic sigmoid. Who has heard of the logistic sigmoid? You haven't heard of the logistic sigmoid. You have heard.
It's like between 0 and 1, like converting like infinite value between 0 and 1.
Exactly. So you remember we covered this on Tuesday with a linear model. You just have a linear model like that. But if you apply the logistic sigmoid, you receive an S curve, right? Which goes between 0 and 1. Yes?
Yeah.
Are we all with it?
How do you spell sigmoid?
Sig, S-I-J, moid, M-O-I-D. It's called the logistic sigmoid. I called it in our previous lecture the inverse logit function because logit is the log odds and the inverse of that undoes the log odds and gives you the probability, right? So inverse logit, logistic sigmoid, right? Okay. So you can take, with the logistic sigmoid, you can take a linear model and turn it back into a probability, right? So, if this is true, then I know that the log odds, right? So the log of pi 1 minus pi is equal just to mu. Are you with me on this? Yes? I see a lot of nods. Are you sure? Is everybody with me on this? If you're not, this is the time to ask. Yes? Okay. So the log odds are equal to mu, and mu is a linear function of the parameters. Okay, we're all with it. Good. So we go back here, right? So the logit of pi, that's why, by the way, it's called logistic regression, right? Because it's on the logit scale. So the logit of pi means the log odds of pi. Who remembers what the homogeneous probability model meant? What does homogeneous mean?
The same.
The same. The same what? For who?
The same expected value for
Mm-hmm.
all the subjects.
Perfect. So the same in the probability Bernoulli case, the same probability of an event happening for every subject, every I. Yes? Is everybody with that? Yeah? So that's the homogeneous probability model, okay? And you can define the homogeneous probability model as a linear function of a constant value. So the constant is the same for everyone. It's the intercept of the logistic regression model, right? And it is beta 0 in here. So you can say in the homogeneous probability model that the logit of the probability of the event happening or the log odds of the event happening are equal to a constant. Are you with me on that? Yes? Everybody on it? Yes. Okay. So now this is my logistic regression coefficient for the intercept. Yes? Now I want to be able to interpret this. And so in order to interpret it, I know how to interpret odds, more or less, right? So if I tell you I have an odds of 2, we mean, roughly speaking, is the event more or less likely to happen than not?
More.
More, right? Because it's above 1, right? So I know how to interpret odds. If I tell you I have a log odds of -3,
Will be less likely.
yes, that's true. But do you know? Could you interpret the log odds in a kind of natural language way, in a familiar way?
I mean, it's going to be 0, or the probability is going to be 0.
Yes, that's correct. So you're doing a pretty good job. But generally speaking, people struggle to interpret log odds coefficients, right? If I tell you I have a log odds of 15, you don't really know what that means. But if I tell you I have an odds of 2, you know that you're twice as likely. An event is twice as likely to happen than not, right? So what do we want to do? We want to go from the log odds scale, which is difficult to interpret, to the odds scale, which is easier to interpret. And the way we do that is by taking the exponential of my probability, my odds, right? So here the log gets cancelled because I take the exponential, and I remain with the odds. And the constant on the right-hand side becomes the exp of that constant. And so what this means is that the exponential of my constant in a logistic regression is the baseline odds of the event happening. Questions about that? Yeah. Yeah. When I am on the log odds, I have the log odds of the event are equal to my constant, my intercept, right? I'm now trying to interpret this intercept in terms of odds. In order to do that, I take an exponential on both sides, so the log cancels because the exponential of a log cancels out, and we have the odds are equal to x of beta 0. So x of beta 0 are the odds of an event happening. Does that make sense? So the exponential of my intercept are the baseline odds of an event happening. Who's confused? Could you explain to me what is confusing about it?
The first step, I don't get to visually see how the graph would look like.
Forget about the graph.
Okay.
Do you understand that you're on the log odds?
No, that's what I don't.
You don't understand what the log odds
Yeah,
means.
what the log odds.
The log
Yes,
odds.
I understand.
So I told you we need the log odds are. I told you we need a linear model to describe a probability.
Yes.
The scale of the linear model is not in probability terms, it is in log odd terms. So that's where we are. So that's why in a logistic regression you have log odds are equal to a linear function.
Yes.
Okay, now I want to go from the log odds to the odds, right?
Yeah.
So I take the exponential of the log odds, and now I'm on the odds scale, right? Does that make sense?
Yeah, but how do you? I mean, I get that exponential, but like, how do you go from something to an exponential? Is it?
You take the exponential on both sides. It's like adding a constant to both sides. Like, or does that make sense?
No, I don't really get how you can make something an exponential.
If I tell you express this in terms of x, what do you do?
That is x.
This is y equals log x.
Yes.
I want a function in terms of x.
That's x divided by y.
I think the confusion, what exponential does is it like cancels out the log basically, so you're just left with x. So if you take the exponential of both, exponential and log cancels out, and you're just left with x.
Right. Oh yeah. Yes.
Yes.
Yeah.
Okay. You should know this. Like, this is not. You should know this. Like, you are computational social science bachelor students. If you don't know this, you have to go read. Okay. This is important. This is the basics. Okay. So you should know this. All right. Exponentials and logs are important. You have to know. Yes.
So if we just take the exponential of the intercept, we have the odds.
Yes.
Okay.
Yes. Exactly. Exactly. So that's what this is saying, right? You're on the log odds scale in logistic regression. You can take the exponential and you end up on the odds scale. The intercept on the odds scale is x of beta 0. So that is your baseline odds of an event happening. Are you with me?
Wait, what do you? I'm confused by the baseline.
Baseline.
Yeah.
In a linear regression model, you agreed with me that alpha was the value of the y when x was 0.
Yeah.
So that's the baseline value of y,
Ah, okay.
right? Yes?
Yeah.
Yeah, and now it makes sense.
Yeah.
Yeah, good. Okay. More questions? No. Okay. So what have we learned? We learned that how do I interpret the intercept in a logistic regression in terms of odds? I take the exponential of the intercept, and now it is the baseline odds of an event happening. Okay? Now we add a binary covariate to this logistic regression model. Okay? So do you know what I mean by a binary covariate? Yes? Who doesn't know what I mean by a binary covariate? Everyone knows. Okay. So a binary covariate, it can take value either 0 or 1, right? So in the linear scale, beta 0 is the value of the log odds of pi when x is equal to 0. Yes? Who didn't understand what I just said? Yeah. So if I set x equal to 0, what is the value of the log odds?
Just the intercept?
Yes.
Okay.
So beta 0 is the value of the log odds when x is equal to 0.
Yeah.
Yes? Okay. So then I want to interpret my intercept, and the same thing happens. So I take the exponential on both sides, and what I find is the intercept, the exp of the intercept, so the exponential of the intercept, is the odds of the outcome when x is equal to 0. Are you with me on this? Yes? Who's not with me on this? Are we all clear? Yeah? Okay. And then I want to be able to interpret the coefficient on the binary covariate. And so the way I do that, let's start here. So the coefficient on the binary covariate can be interpreted as the odds of the event happening when the binary covariate is turned on. So let's do an example. If this were to be college education, for example, this would be the odds of the event happening, let's say voting for Trump, conditional on being highly educated or college educated, relative to the odds of voting for Trump conditional on not being college educated. So it's an odds ratio, right? So beta 1 is the odds of the event happening when the binary covariate is turned on, divided by the odds of the event happening when the binary covariate is turned off, right? And the way you can see that is if you look at this and you say, okay, the odds of y equals 1 when x is equal to 0, I look back at my log odds, right? So if x is, when x is equal to 1, so if x is equal to 1 and I take the exponential, I have beta 0 plus beta 1. Can you see that? Yeah, I get some nods. Who's not with it? So this is my odds of voting for Trump when I am college educated. And this is my odds of voting for Trump when I am not college educated. And it so happens that this is equivalent to the exp of beta 1, which is the exp of my regression coefficient on the binary covariate. Yes? Confusions, questions? This is the right time to ask questions. So please ask questions. Yes?
Could you repeat that last part?
Yeah, so the last part is just, what exactly, sorry?
About the x beta 1?
Yeah, so x, do you agree that when you divide these two things, you get to this?
Yes.
Yes. So then, can you see that this part on top is the same as this?
Yes.
Can you see it? So what is confusing then?
No, I get it.
Yeah? You sure? Okay. Who else is confused? Put your hand up, please. Yes.
I'm confused, as to what is this for? If
Okay.
it's,
Why are you fitting a logistic regression model?
to see if an event is either going to happen or not.
Fantastic. And what are we trying to learn? We're trying to learn about how a specific covariate, let's say being college educated, will make you more or less likely to vote for Trump or to whatever the event is, right?
Yeah.
And so what we're trying to do now is we fit a regression model, and now we want to interpret the coefficients on our regression model. So we want to be able to say being college educated makes you twice more likely to vote for Trump as opposed to not being college educated.
But why would we ever make that division if we can like just take the exponential of the intercept?
No, of course. I mean, the point is that I'm trying to tell you that the exponential of the intercept is the equivalent to this.
Okay.
Yeah?
Yeah.
Okay. Are you with me? Yeah? Okay. A little more complicated. So suppose that was a binary covariate. So now we have a continuous covariate. You know what I mean by a continuous covariate? Yes, some questions. Can you speak up, please? Do you know what I mean by a continuous covariate? What is happening today? Did you guys have a bad lunch or something? What happened? Like, this is a disaster. So, okay, what is a continuous covariate? What do I mean by that?
It can take any number.
Yes, it can take any value between minus infinity and infinity, right? And a binary covariate can only take two values, 0 and 1, right? So an example of a continuous covariate would be, for example, let's say income or something, right? Although income can only take values above 0, but it's continuous in the sense that it's not discrete, right? You can have decimals and stuff like that, right? Are you with me? Yes, okay. So yesterday, you remember on Tuesday, I gave you the example of the guy who worked on an oil rig and who had a bunch of guns, right? You remember that? Yeah, okay. So let's talk about a bunch of guns, right? So this is the number of guns is X, okay? So we're now trying to find out the probability of voting for Trump conditional on how many guns the guy owns, okay? That's a reasonable example. Okay. We have the intercept. The intercept is interpreted as usual. So it's the expected value of the log odds of voting for Trump when I own no guns. Can you see that from there? Yes? Can I get a higher yes?
Yes.
Yes, good, okay. Then I'm now interested in interpreting beta 1. Now, beta 1 is, first I'm going to tell you what it is. It is the odds ratio of an additional gun to the odds of voting for Trump. So it is by how much the factor by which my odds of voting for Trump increase for an additional gun. Yeah? And you should be able to see that this is the case. Here, Z is a placeholder value for just any value, any number of guns. So Z just says, if your Z is 0, then Z plus 1 is 1. If your Z was 10, then Z plus 1 is 11, right? So all this is telling you is the odds of voting for Trump conditional on having whatever value of guns plus 1 relative to whatever value of guns, right? So for an additional unit in guns, your odds of voting for Trump increase by X of beta 1. Yeah.
And this translates also in the probability later. So
Yes.
by how much one gun influenced the probability in the end.
So yes, but there is a caveat, which I'm going to discuss now, which is you cannot turn these odds directly into probability because they don't have an obvious interpretation. I'll describe as to why in a minute. So these are odds ratios, and the odds ratio means by how much an extra gun will increase my odds of voting for Trump. Yeah.
But then in this equation, does every gun add the same amount?
Yes, correct, perfect, exactly. So on the linear scale, it adds, every gun adds the same amount.
But that's not likely, right?
Well, yes, correct. So, but the point being that after I take the exp of it, so after I exponentiate it, now I'm working with odds, right? And the odds are a multiplicative quantity, not a linear quantity, which means if already you have a high probability of voting for Trump, and you multiply it by a large number, you'll get a larger number than if you had a lower probability of voting for Trump. So because we're on the odds scale, the effect of the extra gun is non-linear on the probability. It is linear on the log odds, but non-linear on the probability. You remember we discussed the example on Tuesday of finding out that a guy who is non-college educated, lives in Texas, and works on an oil rig and is white and male, we discovered that he has 15 guns. Well, the probability of him voting for Trump is not going to increase by that much at that point because he's already at 0.99, right? So discovering an extra gun for that guy at the end of the day doesn't give us as much of an effect as if I discovered that about someone who's like undecided, right? So the way that nonlinearity is implemented is through when we squish the linear model onto a probability one, right? Via the inverse logic function here. Yeah. So what do I mean? So first of all, yeah, so if your beta 1 is bigger than 1, it means your odds are increasing for every additional gun, right? If your x of beta 1 is smaller than 1, it means that your odds are decreasing for every additional gun, right? And if your x of beta 1 is equal to 1, then your odds are neither decreasing or increasing, they're just level. There's no effect of an additional gun on your likelihood of voting for Trump. Does that make sense? Yeah? Okay, so the good question that came from the back is, what happens essentially to my odds? So my odds are, as I was saying, a multiplicative odds. So my odds of voting for Trump are I can describe them as the exponential of this linear function here, right? Beta 0 plus beta 1 x1. Yes? You're all with me on this first line. If you're not with me on this first line, please put your hand up and I will explain it. Yes? Okay. So then when I have an addition inside an exponential, that means I can multiply the two exponentials together, right? So then I have the exponential of beta 0 multiplied by the exponential of beta 1 times x1. So I have my baseline odds multiplied by the exponential of beta 1 by x1. So the exponential of beta 1 x1 is the factor by which I multiply my baseline odds. Does that make sense? If my baseline odds of voting for Trump were 70%, now for every additional gun, right, let's say this guy has no guns, then you're at the baseline odds. The guy has one gun, then I take the x of beta 1 and I multiply my odds with it. 2, beta 1 times 2, x of that, I multiply my baseline odds with it. So this is what we mean by logistic regression is like a multiplicative model. Odds ratios are multiplicative. They multiply the baseline odds by a factor, and that factor augments or decreases the probability relative to the baseline. Talk to me. Yeah.
So is the equation considering more that you're either already likely to vote for Trump or not, or that you're already having a gun or not?
So this is the odds. So the left-hand side of the equation is the odds of voting for Trump, right? And now we want to look at whether they increase or decrease as a result of owning an extra gun, right? So then I have my baseline voting for Trump odds, right? And I multiply those by some number, which depends on whether the impact of owning an extra gun is positive or negative, right? So if I have 15 guns, but my impact is very negative, then this is going to be a number very close to 0, and it's going to lead to my all odds to be very, very low, close to 0, right? If beta is very positive, x of beta times x is going to be very large, and it's going to multiply my odds quite dramatically, right?
In which case you're more likely to vote.
Which makes me more likely to vote for Trump, exactly. Questions? Yeah.
I'm still a bit confused what the baseline of a logistic regression is, or like, what is the baseline of a probability, or?
It's the baseline odds, right? So beta 0 is the baseline log odds of voting for Trump.
But what does it mean, like, essentially? Like, what is
The value of the odds for voting for Trump when all the other x's are set to 0.
Yeah, okay.
Right?
Yeah.
So then you have the x of beta 0 is the odds of voting for Trump when all your x's are set to 0. Right? More questions? comments, concerns? No? Are we good? Everybody good? There's still time to ask questions. So if you're confused, if you're thinking, should I ask a question? Please ask a question. Yeah.
Pi
Yeah,
is the probability.
that's correct.
So pi is a variable here?
Pi is the parameter that we're trying to estimate, right? So we want to find out about the probability of voting for Trump.
So,
Right.
so it's variable. It's not a number.
So, like, it's a you can think about it as a variable that we do not know the value of, and we're trying to estimate.
Why is it pi? Because pi is a number, right? So it's a bit confusing.
No, you're thinking of 3.14.
Yes.
Yeah, no. So really?
Yeah.
Okay, guys, pi is a Greek letter, right? If I want it only means 3.14 in the context of like a circle or like a sphere or whenever we need to calculate a radius or a diameter, right? It just means probability. It's the Greek letter for p, right? So pi.
Yeah, okay. It's not the number, but e is the number.
E is the function, the exponential, which means, yes, you take e to the power of whatever is inside it. Yeah?
Yeah.
Okay, good, good. That wasn't a stupid question, by the way. Sorry if I sound harsh. It's just that I'm also trying to understand like what I should highlight in the lecture and what I shouldn't, etc. So it's good that you give me some feedback on that. Thank you. Okay. So, I have some baseline odds of voting for Trump. They are represented by the exponential of my intercept. I have a bunch of guns, and the amount by which any additional gun increases my likelihood for voting for Trump is calculated as the exponential of the impact of any extra gun on the log odds multiplied by the number of guns I have. Yes? Yeah.
So the baseline odds are the odds when what is set to 0?
What do you think? What is there in this model? What could be possibly set to 0 here?
Yeah, I have problems with the terminology here.
So tell me, so what do you think it is? So we have three things here, right? So beta 0 is what we're trying to say it is. So it can be that.
Yeah.
So beta 1 is what?
It's the gradient.
The gradient, yes.
Yeah, the gradient
The gradient of what on what?
of the gradient of x of the variable.
Right. Which means the impact that the variable has on the outcome, right?
Yeah.
You're with me on that, yes?
Yeah.
Yes. So in logistic regression, we are on the log odds scale,
Yeah.
right? So it is the impact that the variable has on the log odds of the outcome, right?
Yeah.
Okay. So if I set x to 0, what is beta 0?
The intercept.
Yes, but when I set it to 0 and I have x of beta 0, what do I recover?
The odds.
Yeah, but don't look at your notes. Literally, just I set that to 0, so this disappears.
Probability.
Then just look at the board. What is this called on the left?
This is the odds.
Correct. And what is this on the right?
Exponential of intercept.
Right.
Yeah.
So the exponential of the intercept
Yeah.
is the odds
Yeah.
when your x is equal to 0.
Yes. But don't I have like many x's?
Right. And then what happens if I have many x's to my intercept? And I set all of those x's to 0.
Yeah.
So what is, even if I have 10 x's, what is my intercept going to be?
The intercept doesn't.
Doesn't change. Exactly. So it's still the baseline odds, right?
Yeah. But I'm confused about something else, but I don't know exactly how to explain it.
Okay.
So we have the baseline probability of voting for Trump, and we have different like predictors of that. It could be the number of guns, which you mentioned, but it could also be I don't know if you're a man or a woman.
Yes.
So what are those called the number of guns that you own. Then
Those are your covariates.
called that-
Covariates, correlates, attributes of the individual, characteristics of the individual. They're just things, regressors, things that are correlated with the outcome.
So it's all of those names describe.
Yes, yes. Covariates, correlates, attributes, characteristics, columns of the design matrix, right? Like,
Okay.
Yeah.
That's what I was confused about.
Good,
because I
good.
was hearing all those different names, and I wasn't sure if they're the same thing.
brilliant.
or not.
So now I'm glad we could clear that up. That's great. That's great. Any more questions on this? No. Okay. Okay, so now a slightly more difficult example is what happens when I have both a binary and a continuous covariate, right? So now I have two x's. X1 is binary, so it's college education. Either you have it or you don't. And x2, what did I say? X1 is binary. X2 is, let's say, your age or something, right? Or the number of guns. Let's take the number of guns because people seem to like this example. I don't know if they like it actually, but anyway. So when I have these, okay, I set my x's to 0, I take the exponential of both sides, and I still recover that my intercept is the baseline odds, i.e. the odds of voting for Trump when I didn't go to college and I have no guns. Yes? Yes. X of beta 1 is the odds ratio of voting for Trump, conditional on having gone to college, and doesn't matter how many, whatever number of guns I might have, over the odds of voting for Trump, conditional on not having gone to college, regardless of whatever number of guns I might have. So it retains exactly the same interpretation with this added snag, which is, and I mentioned it in the last lecture, it is ceteris paribus, which means holding everything constant. So it's the extra amount of the factor by which the odds of voting for Trump increase if you went to college, regardless of how many guns you have. Okay? Yeah.
So does it matter at whatever you set C to? Like it could be 1,000 or
So it
0.5.
can, it could, because you could have a separate, set it to 0, essentially. That's the idea. You set C to 0. In fact, I may even replace this at some point and put that to 0 there. Why 0? If you remember, when I standardize my covariates, right, and I have the average of my standardized covariate, what value do I have? I standardize my covariates. What is the average of those covariates? If I standardize, so first of all, do you know what I mean by standardize? Who doesn't know what I mean by standardize a covariate? Okay, so you know that the formula to standardize a covariate is x minus the mean of x divided by the standard deviation of x. Yes? Who doesn't know this? Who's seeing this for the first time? So if I do this and I recover my standardized covariate x star, what is the average of x star? 0, right? It's 0. So if I have standardized my covariates, setting a value of my covariate to 0 means holding it constant at the average, right? If I have standardized my covariate, right? So typically we hold the value of x constant, okay? Okay, so x of beta 1 is still the odds ratio on voting for Trump if I've gone to college relative to not having gone to college. So by how much does my likelihood of voting for Trump increase if I've gone to college as opposed to not, right? And my x of beta 2 also retain their previous interpretation, which is, for every additional gun, by how much does my likelihood of voting for Trump increase, regardless, holding whether I have gone to college or not, right? Constant. So regardless of that. So what does this mean? This means that these two are independent effects, right? So when one happens, one happens with the same strength, regardless of the value of the other covariate, right? Does that make sense? Yeah? Or not? Tell me, talk to me. If it doesn't make sense, talk to me. Yeah.
For the situation of beta 2, should we set that to 0 as well?
So z can be whatever, right? Because so typically it's set to 0, but that z relative to z plus 1 relative to z just means whatever value of your age, let's say, is, the value of adding an extra unit of age will always be x of beta 2. Right? The increase in the factor of the odds for an extra unit of age is always x of beta 2, regardless of which z you pick. Does that make sense? Yeah. So again, recap. So intercept, always the same. The exp of the intercept gives you the baseline odds. Binary covariate, the odds ratio, exp of beta 1 is the odds ratio of the outcome if college education as opposed to not college education, right? And then the exp of a continuous covariate is the odds ratio of the outcome for one extra increase unit in that continuous covariate, okay? And these are not additive, right? They're multiplicative. So I start with my baseline odds, which could be 0.9, and then I multiply those by my odds ratio for college education, and then I multiply those by my odds ratio for an additional year of age, right? Which is what we do, what we did before. Okay, last thing about this. So interactions. So do you know what an interaction between two variables is? Yeah.
Maybe if they are correlated.
So if that's not quite what it is. So let's say you run a linear regression model, and I want to have one of my covariates be an interaction between two of my covariates. Let's say the interaction between gender and education, right, and college education. How would I get that interaction variable?
You could multiply.
Perfect, exactly. So you multiply the two, right? So the interaction means, can we open some windows, by the way? It's really warm, isn't it? Or is it just me?
No, it isn't.
It's just me.
No,
No, it is warm, yeah. I'm like about to melt it down. Okay, good. So an interaction is just the multiplication of two variables, right? So what does that mean? Let's take again the example of college education and number of guns. If I interact, so I multiply college education, which is 0 or 1, with number of guns, which is 0 to 50 or something, then when I multiply them, I will have 0 for everyone who is not college educated, and then I will have the number of guns for everyone who is college educated, right? That's how that would look like, that interaction, right? That's my interaction x1 times x2 here. And then I want to find out what the impact of the interaction is. The impact of the interaction is the additional effect of an extra gun when you are college educated, right? So it's an additional effect on top of the independent effects of college education and guns. It's the interaction. So it's an additional effect when those two things happen together. Does that make sense? Questions about just generally what an interaction is? Yeah.
Does this mean that because in this case, do you also calculate the addition of not owning a gun and not having college education?
So that's a great question. So where do you think the effect of not owning a gun? So the odds of voting for Trump for someone who doesn't own a gun and doesn't have any college education, where do you think they are here? So if I don't own a gun, my x1 is set to 0.
Yes.
And my x2, if I didn't go to college, the other way around, doesn't matter. If x2 I didn't go to college, it's set to 0 too.
Oh, right. Yeah.
So the answer is?
It's already in there.
It's already in the odds, right? So in the baseline odds, right? So that's when we say relative to the baseline, right? You've heard this terminology before. That's what we mean. So when I have an interaction, the baseline now becomes the baseline odds, i.e. the odds of voting for Trump when both of my x's are set to 0, right? Okay. Good. So how do I interpret my x beta 3? Okay, so again I take the exponential of beta 3 and now I have to interpret it in terms of an interaction. So the way I do that is by saying it is the odds ratio, so it is the factor by which I multiply my baseline odds for an additional gun when I am college educated. Does that make sense?
Could this effect be negative?
Yes, sure. So even if your main effects are positive, absolutely.
But how
Oh, sorry, you mean the x of it, can it be negative?
about the beta 3?
The beta 3 can definitely be negative, yes.
But if beta 1 and 2 are both positive,
Yes.
it's not going to be a negative.
No, absolutely it can. It would mean in that case that individuals who have a lot of guns and are college educated might be very against Trump for whatever reason, but having more guns leads to more vote for Trump. So, so on average, individuals having more guns leads to more Trump vote, but if you're highly educated and own more guns, it might go the other way. Right? That's what the interaction is. It's the additional effect on other than the average effect. Does that make sense? Yeah. And so what's interesting about that is that if you think about it in terms of, again, this multiplication, right? We start with the baseline odds. Then we multiply the baseline odds with the effect of going to college. We multiply that with the effect of owning a gun. And then we multiply that with the effect of owning a gun and going to college, right? So what does that mean? We start, let's say, with 0.7, then we multiply maybe by 0.9, we end up with something lower than 0.7, and then we multiply it again, and then it ends up lower again, and maybe this is really large, right? Maybe your beta 3 is really large, and then you multiply by 2 or 3 or something like that, right? So this is kind of, the beta 3 can off-balance the main effects. Does that make sense? Like, beta 3 doesn't have to follow the main effects. Do you know what I mean by main effect? Who doesn't know what I mean by main effect? Yeah, so by main effect, I just mean the effect of the main effect on the covariance. So this is the main effect of x1, this is the main effect of x2, and this is the interaction effects of x1 and x2. Questions on this? No, okay.
Yeah,
Good.
wait.
Yeah.
When, like, this might be totally out of the
No,
scope,
no, no.
When do you know when you want interactions?
No, this is a great question, actually. So, typically, interactions should be theoretically motivated. The reason is because adding interactions can lead to overfitting, right? So you might have like, if you have 3 variables, you can get an interaction between any 2 of them, and then a 3-way interaction, right? If you have 4 variables, you might get an interaction between any 2 of them, 2 3-way interactions, and 1 4-way interaction, right? And so on and so forth. So what you might end up with is loads of covariates. Your model might get extremely complex. And what we saw from the model assessment lecture is that when your model increases in complexity, your in-sample fit tends to be exaggerated, right? The model is too optimistic. And so it is not advisable to just run a bunch of interactions in your model. They should typically have a theoretical motivation. Now, if you have like a deep learning algorithm or a machine learning algorithm and you have so many observations that you don't know what to do with, you can have the model learn the relevant interactions from the data itself. But typically you can't do that because you need so many observations in order to do that, that it's not feasible. So generally speaking, as far as you're concerned, you should motivate your interactions with theoretical considerations. Good. So, now we've done a little bit now, right? So now you know how to interpret the regression coefficients, you know how to interpret them in terms of odds, right? You've understood that they're multiplicative, but it's hard, right? It's hard work compared to your linear regression stuff, right? It's not as simple as an increase in this and 1 unit increase in that, right? And that sucks, that really sucks. And it gets more complicated when you have more covariates, right? So if I have like 15 covariates, then it gets difficult to conceptualize what does it mean to increase by a factor of 5 when the other variables decreased by a factor of 5. It's just, it doesn't quite fall off the tongue, you know, it's difficult to work with. And generally speaking, people find it difficult to work with odds and odds ratios. So there is something that you can do about that. When your event is really rare, so when it's close to 0, your odds are the same as a probability. So why does that happen? Let's look at the formula for the odds. Pi divided by 1 minus pi, right? If pi is close to 0, then you just have pi divided by 1. So when an event is really rare, your odds are the same as your probability. Yes? Yes? Everybody yes? Yeah. Okay. So that's one thing. But generally speaking, you can't do that. And there is an added problem. So you can only do that when your pi is rare. And there's an added problem, which is called non-collapsibility. So I'm just going to give you an intuition for it. You don't need to understand exactly what it does. But let me ask you this. Suppose I have a logistic regression model with one covariate in there, namely college education. Okay? And then I tell you, I estimate the coefficient for college education. I get 3, let's say, right? And now I tell you, I'm going to add another covariate to my model that has absolutely no correlation with college education whatsoever. It is totally independent of college education. Do you expect, this is my question to you, do you expect the coefficient on college education to change after I add that covariate?
Yes.
You say yes. Why?
Because when you have one coefficient, it's already a complete model, so if you add another variable, you have to somehow balance it.
So that logic is exactly the reason why it doesn't work for logistic regression. So why in linear regression, if you add an uncorrelated covariate, your coefficient should not change, right? Because the covariate is totally uncorrelated. So the outcome is linear, so there is no reason why the addition of an uncorrelated covariate should change the covariate that is independent of it. The problem in logistic regression is that because the amount of variance to be explained is fixed in some sense, adding another covariate, regardless of whether it is correlated with the original covariate, will change the coefficient on that covariate. And that is a problem, because it means that if I have two models, both containing college education as a covariate, but one of them including another variable, even if it's irrelevant, I cannot compare the coefficients of college education between these two models. They're going to be on different scales, essentially. So this is an issue. And that's one of the reasons why people don't like logistic regression. Because if I add irrelevant covariates, the coefficients of my relevant covariates will change, even though they're supposedly completely unrelated to the covariates that I just added. Right? And why is that a problem? Because if my coefficient on my relevant covariate changes, it would suggest in my mind that there is a relationship between my covariate and the one that I just added. But this is just not true, right? By definition, it's not true. Okay, so this problem of non-collapsibility basically leads to problems of interpretation. You don't need to exactly understand why non-collapsibility arises, but you should understand like what the implications are. The implication is, if I have a model with one covariate, and then I fit the same model with that covariate and another, I cannot compare the values of, I can't say, for example, adding this covariate led to a 3% increase in my intercept. I cannot say that, because they're on different scales. This is non-collapsibility, and it's a problem of logistic regression, right? So I can only compare coefficients once I have my full model, and I'm stuck with that. Okay? Okay. So that sucks, and it's difficult to work with odds and odds ratios. So something that we can do instead is work with, we're almost done by the way guys, and then we're going to take a break, and then we're going to do the workshop, and I'm here to answer questions, etc. Okay, so we're almost done. So because it sucks so much to work with odds and odds ratios, and logistic regression has all these problems, and it's difficult to interpret, etc., there is an alternative. Okay, so I want you to look at my board now instead of the screen. So what I can do instead is, so does this not work? So you understand that by applying the inverse logit to beta 0 plus beta 1 xi1, I recover a predicted probability for this individual. Yes? Who doesn't understand what I just put on the board? Put your hand up, please. So I have an individual. This individual has some characteristics. Let's say he's college educated, right? And then I estimate a linear model, and then I take the inverse logic of that and I make a prediction in terms of probability for that individual. So this gives me the probability that this individual will vote for Trump. Yes? Yes. Okay. What I can do is I can make up a reference individual. So I can say, let's take the average American, okay? And so somebody with an average level of education, okay? And then I can make a prediction for the average American in terms of his probability of voting for Trump. The bar above means the average, okay? So I just took the average of the variable college education, right? And I'm now making a prediction for the probability of the averagely educated individual in America. Does that make sense? Yeah. I can now do my prediction for another individual, any other individual. Right? So this is just another individual I, okay? And if I want to find out what impact relative to the average having a high level of education has, I can simply replace the value for X to be high educated. So this now gives me the probability of an individual voting for Trump if you're highly educated. And then I have the probability of voting for Trump for the average American. And now I can calculate the risk difference between the two. So I can say the probability of voting for Trump if you're highly educated minus the probability of voting for Trump for the average American. And this is my measure of education, right? It is more easily interpretable than odds, right? It's just, here is my probability for the average American. Here is the probability for a highly educated American. The difference between the two is the impact of education on the vote relative to the average. Questions about this? Yeah?
Education here is on a continuous scale, right?
You can also make it 0 or 1. It doesn't matter. So this could be education high, could be 1, education low could be 0.
And what is the average?
It's, let's say I have a sample of 1,000 people, and the average of this 1, 0 variable is 0.2. It means 20% of the people have high education in my sample.
Okay.
So the average would be somebody who is 0.2 educated, which in itself doesn't mean much, but it's still the average, right?
Mm-hmm.
If you wanted instead to compare to someone who is low educated, instead of your reference, instead of using the average, could use low, right? So you could set your reference to have x equals 0, and then make the prediction, right? Now, what's nice about this is that, okay, and yeah, so we calculate the risk difference, right? And then the other measure that we like to calculate is the relative risk, which is just my relative probability of voting for Trump if I'm highly educated relative to the reference, right? So what would the outcome of this? The outcome of the above would be like, somebody who is highly educated has 5% higher probability of voting for Trump than the average. And then the outcome at the bottom would be like, somebody who's highly educated has 1.2 times the probability of voting for Trump than the average. Does that make sense? Yeah? Okay, that's great. So the cool thing about this is that you can do this for any level of complication. So let's say now we add another covariate, B2, which is the number of guns, again, right? And so I can now hold it for the average number of guns, right? And then here I can start making what are called counterfactuals. So I can say, okay, let's imagine a guy who has high level of education and a low number of guns. And let's get its prediction. So that's high level of education, low number of guns. And then let's do it again, but this time, let's do high level of education and high level of guns, right? And then I do another one of these. This time, instead of setting X to low number of guns, I set it to high number of guns. And then what I get now is a series of predictions, right? I have the predicted probability for a guy who has high level of education and low number of guns, the predicted probability for a guy who has high level of education and high level of guns, the predicted probability for a guy who has low level of education, low level of guns, and the predicted probability for a guy who has low level of education, high level of guns. And for each one of these, I can compare them to the average, right? And I can make inference. I can say, this guy has twice the probability of, owning a gun when you are low educated increases your odds for voting for Trump by this much. Owning when you're not educated decreases your odds by this much, and so on and so forth. Does that make sense? Question, yeah?
This relationship is not linear, which means if you compare the low gun value with the averages, the difference is not going to be the same.
No.
Compared with the...
That's right. That's right.
Yeah, so if you have a continuous variable like from 0 to infinity gun, you just have to have a different value for each.
Yeah, but you wouldn't. Perfect. Yes. So the answer is yes, but you wouldn't. You don't need to pick every possible value of guns. You can just pick like through, low, medium, high, for example, and then you can plot that curve, and then that will be enough.
Okay.
Yeah. So it's like scenarios. You're doing counterfactual scenarios. So you're like, okay, if I have a low number of guns and a high education and I'm a woman, what is my probability? And then, what about that same thing, but if I'm a man? And what about, and then you can compare. And you can, by doing these comparisons, you can find out about the effects of having or not having these covariates. Does that make sense? Yeah. Okay. We made it. So that was hard, guys. Holy moly.